Hello everyone, today we will find an expression for power spectral density of random process obtained at the output of an LTI system in response to an input random process xt. Before proceeding further, let's have a quick recap. In the last class, we discussed about the statistical characterization of random process obtained at the output of an LTI system in response to an input random process xt. So consider an LTI system with the impulse response ht. Now the input to the LTI system is the random process xt and the output from the LTI system will be the output random process yt. Now we know that what is the relation between xt and yt? Yt is xt convolution ht. Now the mean of the output random process, that is mu y, is given by mu x into h of 0. That is, the mean of the output random process will be equal to the mean of the input random process multiplied by the DC response of the system or zero frequency response of the system. Now autocorrelation function of output random process Ry2 will be equal to double integral minus infinity plus infinity minus infinity plus infinity h tau 1 h tau 2 Rx tau minus tau 1 plus tau 2 d tau 1 d tau 2. Now we know that the mean square value of output random process, that is expectation of y square t, will be equal to the autocorrelation function evaluated at tau equal to 0, that is Ry0, which will be equal to double integral minus infinity plus infinity minus infinity plus infinity h tau 1 h tau 2 Rx tau 2 minus tau 1 d tau 1 d tau 2. So let this equation is equation number 1. Now we know that the impulse response of an LTI system and frequency response are Fourier transform pairs. That is, impulse response and frequency response are Fourier transform pairs. Oh, I will write like this: impulse response and frequency response of an LTI system will be their Fourier transform pairs. That is, frequency response of an LTI system can be defined as h of f equal to integral minus infinity plus infinity h tau e raised to minus j 2 pi f tau d tau. Now the impulse response of the LTI system can be written as h tau 1 is equal to the inverse Fourier transform of frequency response, right? Integral minus infinity plus infinity h of f e raised to j 2 pi f tau 1 df. That is, impulse response of the LTI system will be the inverse Fourier transform of the frequency response of the LTI system. Now we will substitute equation number 2 in equation number 1. We know that the mean square value of output random process will be equal to double integral h tau 1 h tau 2 Rx tau 2 minus tau 1 d tau 1 d tau 2, assuming xt as w as random process. Now we will substitute h tau 1 by equation 2. We know that h tau 1 is integral minus infinity plus infinity h of f e raised to j 2 pi f tau 1 df. So that is integral minus infinity plus infinity. Instead of h tau 1, I will write it as h of f df, and remaining e raised to j 2 pi f tau 1 is there. Integral minus infinity plus infinity h tau 2 e raised to j 2 pi f tau 1 Rx tau 2 minus tau 1 d tau 1 and d tau 2. So we have one more integral is there, integral minus infinity plus infinity, because this integral will be the integral corresponding to this h tau 1. Okay. Now I am replacing tau 1. We know that tau equal to tau 2 minus tau 1. Now tau 1 can be written as tau 2 minus tau. So we know that tau 1 equal to tau 2 minus tau. So I am rewriting this particular equation. Integral minus infinity plus infinity h of f df integral minus infinity plus infinity h tau 2 e raised to j 2 pi f tau 1 is tau 2 minus tau d tau 2 integral minus infinity plus infinity rx tau 2 minus tau 1 d tau 1. So we know that tau 2 minus tau 1 is tau. Okay. So I am going to split this particular quantity as e raised to j 2 pi f tau 2 into e raised to j minus j 2 pi f tau. And this quantity is clubbed with this integral, and only this quantity is clubbed with this particular integral. So this can be written as integral minus infinity plus infinity h of f df integral minus infinity plus infinity h tau 2 e raised to j 2 pi f tau 2 d tau 2 integral minus infinity plus infinity rx tau e raised to minus j 2 pi f tau d tau 1. Okay. Now we know that tau 1 equal to tau 2 minus tau, and we need to replace this integral with respect to tau. So with respect to tau 1, tau 2 is a constant. So d tau 1 can be written as minus d tau. Also, when tau 1 equal to minus infinity, tau equal to plus infinity. When tau 1 equal to plus infinity, tau equal to minus infinity. So equation number 2. This is equation number 3. Now 3 can be rewritten as integral minus infinity plus infinity h of f df integral minus infinity plus infinity h tau 2 e raised to j 2 pi f tau 2 d tau 2 integral. So this is in this integral the variable of integration is tau 1. This is tau 1 equal to minus infinity plus infinity. Now we need to replace this variable of integration by tau. So tau equal to plus infinity to minus infinity rx tau e raised to minus j 2 pi f tau minus d tau. So now I will absorb this minus to this particular integral. So this integral becomes minus infinity plus infinity. So this will be equal to integral minus infinity plus infinity h of f df integral minus infinity plus infinity h tau 2 e raised to j 2 pi f tau 2 d tau 2 integral tau equal to minus infinity plus infinity rx tau e raised to minus j 2 pi f tau d tau. So this is equation number 4. That is, this is expectation of y square t. So here we can see that what about this quantity? This quantity is h tau 2 e raised to j 2 pi f tau 2 d tau 2 minus infinity plus infinity. So we know that impulse response is, frequency response is h of f is integral minus infinity plus infinity h tau e raised to minus j 2 pi f tau d tau. Here we can say it is plus j. So this quantity will be, we can write it as h star f. Now what about this quantity? So we can see that integral tau equal to minus infinity plus infinity rx tau e raised to minus j 2 pi f tau d tau. So we can call this as Fourier transform of autocorrelation function. The Fourier transform of autocorrelation function, we will call it as power spectral density. So expectation of y square t can be written as, so integral minus infinity to plus infinity h of f df into h star f into integral minus infinity plus infinity. So instead of minus infinity plus infinity, we can write this as sx of f. What is this sx of f? We will call it as Fourier transform of autocorrelation function, which is called power spectral density. So this can be written as, thus mean square value of output random process will be equal to integral minus infinity to plus infinity mod hf square sx of f df. We know that h of f into h star f will be equal to mod hf square, where sx of f is called the power spectral density of random process, power spectral density of the input random process xt. So this is equation number 5. Now equation 5 states that the mean square value of the output of a stable LTI system in response to the Whiteson stationary random process xt is equal to the integral over all frequencies of the power spectral density of input random process multiplied by the squared magnitude of the transfer function of the filter. Now coming to properties of power spectral density. We know that power spectral density and autocorrelation functions are Fourier transform pairs. That is, Sx of f equal to integral minus infinity to plus infinity Rx tau e raised to minus j 2 pi f tau d tau. And similarly, autocorrelation function will be the inverse Fourier transform of power spectral density function. Integral minus infinity plus infinity Sx of f e raised to j 2 pi f tau df. So this is equation number 6 and this is equation number 7. Equation 6 and 7 we will call it as Einstein-Wiener Khinchin relation. Einstein-Wiener Khinchin relation. Now coming to the first property. Property number 1. The zero frequency value of power spectral density of Whiteson stationary random process is equal to the total area under the graph of autocorrelation function. That is, we know that Sx of f is integral minus infinity plus infinity Rx tau e raised to minus j 2 pi f tau d tau. So the zero frequency value of power spectral density means put f equal to 0. That is, Sx of 0 equal to integral minus infinity plus infinity Rx tau d tau. That is, the zero frequency value of power spectral density of Whiteson stationary random process is equal to the total area under the graph of autocorrelation function. Now coming to property number 2. So we know that the autocorrelation function evaluated at tau equal to 0 will be equal to the mean square value. That is, when tau equal to 0, we will get it as Rx of 0 equal to integral minus infinity plus infinity Sx of f. This is tau equal to 0. So integral minus infinity plus infinity Sx of f df. That is, the mean square value of a Whiteson stationary random process is equal to the total area under the graph of power spectral density function. That is, expectation of x square t equal to Rx of 0 equal to integral minus infinity plus infinity Sx of f df. That is, the mean square value of a Whiteson stationary random process is equal to the total area under the graph of power spectral density function. Now, last property is the power spectral density of Whiteson stationary random process is always non-negative. So, there are three properties. Property number 1, Sx of 0 is area under autocorrelation function. Then property number 2 is area under power spectral density function will be equal to the mean square value. And property number 3 is the power spectral density of a Whiteson stationary random process is always non-negative. That is, property number 3 is Sx of f greater than or equal to 0. Since the mean square value is always non-negative. Thank you.